Om Swastiastu, Assalamualaikum warahmatullahi wabarakatuh. Shalom, salam sejahtera bagi kita semua. Today I want to presentation my PowerPoint. The title of my PowerPoint is Nonferrous Metals, a Variety of Possibilities. Now I want to introduce myself. My name is Jessen Lubis. I'm from Metalurgi, Mechanical Engineering, Udayana University. Main reference from Metalurgi for the Non-Metallurgist second edition, edited by Arthur Riordan. Compared with their steel counterparts, non-ferrous metals and alloys are notable in their number and in the diversity of their properties. Many non-ferrous elements do double duty as important alloying agents for both steels and non-ferrous metals. For example, virtually all steels contain small amounts of magnesium, which is used mainly to control and in some cases counteract the undesirable effects of sulfur and to aid in achieving hardenability requirement. 1. Light metals. Aluminium as a light metal. Aluminium has a density of only 27 G or cm3, resulting in a weight that is approximately one-third that of the same volume of steel, copper, or brass. Such light weight, coupled with the high strength of certain grades of aluminum alloys, permits the design and construction of strong, lightweight structure. Aerospace structure are a primary example of this. Aluminum alloys hold the distinction of being of the material of choice in the construction of aerospace structure, such as airplane fuselages and wing components and rivets. Beryllium is a high-strength, lightweight metal that is pending increasing use as a structural material in aerospace vehicles. The density of beryllium is only 185 G or cm3. This is low density coupled with the strength give beryllium an outstanding strength to weight ratio. Magnesium has long been recognized as the lightest structural metal. Structural applications include industrial, materials handling, commercial, and aerospace equipment. In industrial machinery, such as textile and printing machines, magnesium alloys are used for parts that operate at high speed and thus must be lightweight to minimize interior force. Titanium is another low-density element that can be readily strengthened by alloying and deformation processing. Like steel, it is allotropic. Titanium makes it in two crystallographic forms. At room temperature, annealed titanium has a hexagonal close-packed crystal structure referred to as alpha phase. 2. Corrosion-resistant alloys. Cobalt is used as an alloying element in alloys for various applications such as permanent and soft magnetic materials, superalloys for creep resistance at high temperature, hard facing and wear-resistant alloys, corrosion-resistant alloys, high-speed steels, tool steels, and other steels, cobalt-based two materials, electrical-resistant alloys, high-temperature spring and bearing alloys, magnetostrictive alloys, special expansion and constant modulus alloys, and biocompatible materials for use as orthopedic implants or dental materials. Copper is a noble metal, but unlike gold and other precious metals, can be attacked by common regions and environments. Copper and its alloys are unique among the corrosion-resistant alloys in that they do not form a truly passive corrosion-product film. In aqueous environments at ambient temperatures, the corrosion product predominantly responsible for protection is a adherent copperous oxide layer. Nickel alloys are very important to industries that deal with aggressive chemicals and high temperature conditions. Many of the nickel alloys designed to resist aqueous corrosion pose higher resistance to hydraulic acid and chloride-induced phenomena than the stainless steels. Titanium and its alloys are part of large family materials known as the reactive metals. All of the reactive metals, notably titanium, zirconium, niobium, and tantalum, benefit from highly protective oxide films. As a result, their corrosion rates are extremely low in many environments. Aluminium. Like titanium, aluminium and its alloys are protected from many potentially corrosive environments by oxide films that form readily on freshly exposed surface. Aluminium has high resistance to corrosion in atmospheric environments and in many industrial solutions. Superalloys. Superalloys are intended to prevent or minimize screw deformation at high temperature. They all have a face-centered cubic structure. Iron and cobalt both undergo allotropic deformation and become FCC at high temperature or white alloying. Nickel, on the other hand, is FCC at all temperatures. In superalloys based on iron and cobalt, the FCC forms of these elements generally are established by alloying addition. Alloying elements include chromium, molybdenum, vanadium, cobalt, and tungsten. Next, refractory metals. Molybdenum has a relatively high melting temperature of 2610 degrees Celsius, along with a high modulus, good grip strength, and the retention of mechanical properties at high temperatures. Molybdenum is primarily used as an alloying addition in iron, steels, superalloys, and corrosion-resistant alloys to improve hardenability, toughness, abrasion resistance, strength, and resistance to creep at elevated temperature. Niobium. In addition to its high melting point, niobium is used for its combination of relatively lightweight and retention of high strength at surface temperature ranging from 980 to 1205 degrees Celsius. Niobium alloys are also used to impede the passage of neutrons in nuclear applications. Rhenium. The properties of rhenium are generally similar of those of molybdenum and tungsten. Its melting temperature of 3180 degrees Celsius is the second highest among the refractory metals. Pure rhenium combines superior room temperature ductility with good high temperature strength. It is used in combination with tungsten in the production of high temperature thermocouples. Tantalum has a melting point of 2996 degrees Celsius and high resistance to corrosion, including corrosion in body fluids. The largest usage for tantalum is as powder and in notice for electronic calculators. device that the electrical change when voltage is applied. Another important use is in prosthetic device and surgical staples. Tungsten. An extremely dense metal is an excellent alloying agent. The major of in tungsten is in carbide metal cutting tool, and where resistant materials in these materials hard carbide particles are bound together or jammed by a shock of ductile metal bender such as cobalt or nickel. Low melting point metals. Bismuth is brittle, easy to cast, and not readily formed by standard working methods. Its melting point of 183 degrees Celsius is lower than that of thin lead solder. Bismuth is one of the few metals to increase in volume upon solidification. It is diamagnetic and has a low capture cross-section for the thermal neutrons. Indium is one of the softest metals, easily scratched and highly plastic. It melts at 156 degrees Celsius, has low tensile strength and hardness, and is stable in dry air at room temperature. It is neither a toxin nor a skin irritant. Lead. The properties of lead: high density, a low melting point, corrosion resistance, malleability, unusual electrical properties, and the ability to form useful alloys and chemical compounds combined with its readily available forms and relative low cost make it a unique material for solving a variety of problems. Tin. One of the first metals known to humans, is non-toxic, soft and pliable, and suitable for cold rolling. Tin resists corrosion, making it an ideal coating for other metals. Tin has a low coefficient of friction, and the addition of alloying elements such as copper, antimony, bismuth, cadmium, and silver increase its hardness. Jeans has a relatively low melting point of 419 degrees Celsius, resists corrosion, is ductile and malleable, and is highly soluble in copper. As a coating, jeans provides corrosion protection for iron and steel. It is widely used in die casting parts for autos, household appliances, computer equipment, and building hardware. Next, reactive metals. Reactive metals readily combine with oxygen at elevated temperature to form very stable oxide. Reactive metals are extremely noble because of their passive films. However, they may become embedded by the industrial abrasion of oxygen, hydrogen, and nitrogen. Hydrofluoric acid rapidly take reactive metals such as niobium, tantalum, zirconium, and titanium, either as pure or alloyed metal. Beryllium, titanium, niobium, tantalum, hafnium, and zirconium are considered reactive metals. Next, precious metals. 8 metals are in this family. 2 of them, gold and silver, require little or no introduction. Gold is extremely soft, ductile, and easy to deform. Silver. Among metals, pure silver has the highest thermal and electrical conductivity. Next to gold, it is the ductile. Platinum group metals are expensive and scarce. 1. Platinum. Platinum has a high melting point of 1770 degrees Celsius, Remarkably resistant to corrosion and chemical attack, it retains its mechanical strength and resistance to oxidation in air even at elevated temperatures. Platinum has catalytic properties and is easily worked when heated. Palladium has high electrical resistivity. It melts at 1522 degrees Celsius, is very ductile, and is slightly harder than platinum. Iridium has a melting point of 2455 degrees Celsius, which is higher than that of platinum. Rhodium is an important element in high temperature application up to 1650 degrees Celsius. It is very hard and difficult to work. Ruthenium has high hardness and electrical resistivity. Its melting points to 1500 plus 100 degrees Celsius. Osmium has the highest specific gravity and the highest melting point of all the platinum group metals. Next, rare earth metal. Rare earths make up a closely related group of highly reactive metals, which mean they readily combine with oxygen at elevated temperatures to form very stability oxide. Yes. The term rare earth is deceptive. Rare earths are not necessarily rare. The name derives from oxide minerals in which they are discovered. The family tree has these members: scandium, yttrium, lanthanum, cerium, praseodymium, neodymium, promethium, samarium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, and lutetium. Next, metalloids or semimetals. There are some elements that act as metals under some circumstances and act like non-metals under different circumstances. Silicon, used in industry, can be classified into metallurgical and semiconductor grades. Metallurgical grade silicon is the reduction of sun in an electric furnace. It contains approximately 98% Si. Metallurgical grade silicon is used primarily in the aluminum, steel, and silicon industries. 2. Gallium. The chemical properties of gallium are between those of aluminum and indium, and like these elements, gallium is considered to be a non-toxic substance. 3. Germanium is hard metallic elements with a lower melting point than silicon, which result in fabrication properties below 600 degrees Celsius. Germanium has good resistance to oxidation. Above that temperature, oxidation process rapidly. Next, special purpose metals and alloys. Uranium is a moderately strong and ductile metal that can be cast, formed, and welded by a variety of standard methods. It is used in nuclear application largely because of its high density. Uranium and its alloys generally are considered difficult to machine, requiring special tools and conditions. Vanadium. melting point of vanadium is 1900, chemically active and closely related to niobium, tantalum, titanium, and chromium. Vanadium is soft, ductile, and strong, and has good resistance to atmospheric corrosion and to hydraulic and sulfuric acid environments. Magnetic alloys. Magnetic materials are broadly classified into two groups with either hard or soft magnetic characteristics. Soft magnetic materials become magnetic by relatively low strength magnetic fields, and when the applied field is removed, they return to a state of relatively low residual magnetism. Electrical contact materials. Electrical contacts are metal devices that make a break electrical circuits. Contacts are made of elemental metals, composites, or alloys that are made by melt cast method or manufactured by powder metallurgy process. Thermocouple materials. Accurate measurement of temperature is one of most common and vital requirements in science, engineering, and industry. Low expansion alloys are materials with dimensions that do not change appreciably with temperatures. Alloys included in this category are ferrous binary, iron nickel alloys, and several ternary alloys or iron combined with nickel chromium, nickel cobalt, or cobalt chromium alloy. Some memory alloys have the ability to undergo deformation at one temperature and then recover to their previous uniform shape simply by heating or cooling. For example, one common shape memory alloy is a nickel titanium alloy that can be deformed at one temperature but recover its previous uniform shape simply by heating and the alloy above its martensitic deformation temperature. And the last visible alloys include a group of binary, ternary, quaternary, and quinary alloys containing bismuth, lead, tin, cadmium, and indium. That's all from me, and I say thank you.